Okay. Hi, I'm Matt Mazloff from Scripps Institute of Oceanography. Very pleased to be here. Thank you, everyone, for the chance to share with you what I've been working on with Ariane Verdi, and of course, people in the ECHO Consortium and the SOCCOM project. I really liked the theme about estimating the normal, determining the normal. So what we're trying to do, we're trying to understand just what the Southern Ocean properties are, especially the biogeochemical properties, what are the seasonal cycle and the large-scale structure. And so I'm not going to really hit any important science questions today. What I really want to talk about is what are the value of the SOCCOM observations? What are we getting from these data? And then what is the state estimate? And what do I spend my time on trying to, and how are these data informing that? So I hope to get that across today. First off, the SOCCOM array has revolutionized the amount of observations we have, the number of biogeochemical constraints that you can use to make maps or estimates of what the normal state is. In 2007, there was a large deployment of floats with oxygen sensors, and so you see the numbers ramping up through 2009. This is oxygen profiles, number of profiles per year, 2000. Then the floats slowly start dying, and there was no redeployments until SOCCOM started in 2014, and they start ramping up again. When SOCCOM started, we also started getting pH profiles, first 309, then 564 per year, and in 2017, I counted 1,600 profiles from the SOCCOM floats per year. Same thing with nitrate. There was a few floats deployed with nitrate sensors. Now there's 2,000 observations coming a year. Just to put that in context, we get a few hundred profiles from ships each year. And SOCAT gives us quite a lot of observations. This is kind of the SOCAT misfit to our state estimate, or our misfit to the SOCAT data. But it's just surface, and so it's incredibly useful, and it's an incredibly important part of the observing system. But now we're filling in the 3D structure. So what I do is I work on mapping data, and there's really many flavors. There's a whole continuum, a whole spectrum of complexity, from statistical mapping, which we often call objective mapping, or optimal interpolation, or kriging in other fields, to numerical models used. Basically they're the same as statistical models, but we're propagating the information, we're propagating the statistics with a general circulation model, to nonlinear neural networks, machine learning. So there's a spectrum of complexity, there's a spectrum of human versus machine learning. In reality, we'd like to use all these tools, but they are just tools, and we have to be very wary of them. And so to kind of point out that this is, Ken Johnson put the float oxygen values into ODV, and apparently that has an optimal interpolation routine, and you press go, and these are the kind of maps he got. And from human learning, from spending some time here at Hui, many years actually, trying to finish a PhD, I know that the Southern Ocean doesn't look like this. We don't have this kind of structure in the Weddell Sea. And from a statistical background, you know to be wary when you're doing interpolation of maxima between the data points. So we know there's some big problems with that. Yet you can make pretty maps. So it's kind of fun. But what we want to do is actually make maps that aren't just relying on prior information, that have information about where land is, what's going on with the actual ocean. So what we do is use general circulation models to provide the prior and to provide the propagation statistics. Now, there's two real ways of doing this. There's iterative methods and then smooth methods, or what we call state estimates. When you have an iterative method, what you do is when an observation analysis period comes along, you kind of nudge to the data. This is what's done in numerical weather prediction. This is what's done in reanalysis. You have more controllability, right? You're nudging the solution, so you're getting closer to the data. You look really good compared to the dependent data. Although this unphysical nudging can kind of mess up your statistics and can kind of make you less consistent with the independent data. State estimate, what you do instead is you say, I'm going to have one long assimilation window. Instead of just assimilating daily increments and patching them together, I'm going to do a long state estimate. It's the same software as iterative methods. You can use common filter or adjoint method or some combination. But the idea is to get one solution that's true to the physics. And the advantage is then you can understand why you have the front where it is. You have full attribution. You know, why is the nitrate front here versus there? But you have less controllability, so you don't look as close to the data you're simulating. Whereas iterative methods, you're going to get closer to the data. The nitrate front's going to be exactly where you're observing it, but you might not know why. We've chosen for SOCCOM to do the smoothing part, to the state estimate. To kind of drive that home, I don't want to spend too much time, but this is ERA. This is a reanalysis kind of evaluation. This is ERA interim heat flux, the atmosphere. This is the ECMWF, so kind of comparable reanalysis from the ocean. The little green thing is what they estimate to be the total ocean heat, is what the total ocean heat gain is, whereas the blue square is the diagnosed heat flux, and the heat into the ocean from just the analysis increments is the same size as what's going on from the heat flux. So when you see a reanalysis, and also note that the reanalysis ECMWF, the area interim, heat flux is not matching this blue box exactly. So when you see reanalysis, you should know that they might look a lot like the observations, but they don't have closed physical budgets. Now to get a closed physical budget, we use a general circulation model. Here we're using the MIT general circulation model. And we needed a biogeochemical model. We adapted the BLING, biogeochemical light, iron, nutrient, something, biogeochemical model that we got from GFDL. And we also added, it had 6 prognostic tracers. We added nitrate as well. And so I'm told I'm not supposed to call this BLING V2 because they're calling it BLING V2 and they can't change the name. So I'm supposed to, so I would suggest, Brendan Carter said I should call it NBLING or enabling, but I was told yesterday from Keith Lindsay I should just call it West Coast BLING. But this is the model. It's intermediate complexity because data simulation is computationally intensive and we don't want to do too much. So we only have 3 phytoplankton classes. But it's enough to try to get started and fit the data. How we do it is we run the model forward, just a free-running model solution. We compare it to all the observations. We get an estimate of the state. Then we run what's called the adjoint model, which is the derivative of the misfit to all this data with respect to what we're going to control. So we're controlling the initial conditions, the atmospheric state, and what this gives us is the sensitivity of our misfit. So basically, you want to fit oxygen better here, you should make the atmosphere a little colder up here. It just tells us that we systematically make the atmosphere colder there, we change things a little bit, within the uncertainty, and we just do this over and over and over again. Turn the crank, and we get closer and closer each time, a couple % closer to the data. That's the gist of it. BGC Argo is achieving substantial in situ coverage. It now kind of makes sense to do biogeochemical simulation. We have enough constraints. As I'm going to show kind of for the rest of the talk is the value of these data. We have enough constraints now where we can see where we're doing good and where we're doing poorly. And I'll focus more on where we're doing poorly because it's kind of more interesting. But it's really, we have enough now to really validate these models. And what we want to do is produce a gridded data set that's consistent with model physics, and we know where it's fitting the data and where it's problematic, and we want to make it easily accessible, and we want to estimate the normal. And we have this framework to understand the normal because we have closed physics. We produced a 2008 to 2012 biogeochemical state estimate at 1/3 degree. The main biogeochemical constraints on that are the in situ oxygen observations. That was kind of a proof of concept, getting this whole thing working. Now we're working on the SOCCOM era biogeochemical Southern Asian state estimate. Right now we're 2013, 2017. We'll soon add 2018, 19, and we're doing that at 1/6 of a degree. This is the interim solution from that, and it's I don't know how to play movies. Do you know how to? That's my cursor. It's not. Oh, whoops! I'm on the wrong page now. What have I done? Oh, there it is. Okay, so what I'm going to show several plots like this, and this is, we're just quantifying this, just getting the RMS differences, but you can also look, shows you kind of the coverage of the Argo array. Each of these little colored, each of these circles with white borders is the Argo data, and the background is for the model, and for here is for the Remick-Gilson maps. It's hard to see all the observations because we're doing pretty well at fitting them. But we can do the same thing for, I know you probably saw some of them. We can do the same thing for oxygen. Now here's World Ocean Atlas, which is currently arguably the best product, and here's what we've put out now. And you see the deployment of the SOCCOM floats, and it gets a little easier to see some of these things. But one thing you'll notice is that World Ocean Atlas is optimal interpolation, and they suffer from some of those aspects. So even though they're fitting the data as well as us, they're not necessarily, and in some cases better than us, they're not necessarily giving the physical structure that you would want. This is the prior solution in this is a model solution. It's a hypothesis that, it's consistent with physics, whereas this is more of a statistical map. So this is why we like our first guess, but of course we want to fit the data is the most important thing. Now when the bar gets set real low is when you start looking at pH. This is GLODAP. This is the pH product. It's static. It's one mean. It really represents the summer. Whereas, we're doing this full simulation with pH. We now have pH measurements from floats coming in. They're evolving in time. They have a seasonal cycle. And our best guess, pre-SOCCOM doesn't have a seasonal cycle. It's clearly missing what's going on. This is really the value of the floats and the value of being able to now assess what our product's doing year-round. What was really important about this whole production was to make sure that we had documented validation. When I first used to do state estimation, I'd keep all this validation to myself, and then it got lost, and everyone would ask me for it, and it was a pain. Now we're just doing semi-automated validation on a website. You can see compared to satellite data, mapped products, other inferences, lots of different validation. Anything you want to see, we'll add to this. It's all, I press a button and it just spits out all these nice HTML pages. And it lets us see where we're doing poorly, where we're doing well. What we're learning from this is that the state estimate is, as we'd expect, somewhat of a low-pass filter. Here, for example, we have the PCO2 Drake Passage time series. It's the black line. This is really the best time series you're going to get in the Southern Ocean. Is this Drake Passage repeat. It's like 4 or 5 profiles a year. To the black line goes through the summer bloom. This is PCO2 and the summer bloom, summer drawdown is kind of shaded here. What you see is the red, dark red is where we're subsample exactly where the observations were taken, and we're following it pretty well, but we're not getting the extremes as well. So first thing is that it's doing all right with the variability, but it's not getting the extremes, so that's something to learn about. Now I say it's not getting the extremes. It does have a huge amount of variability. Here's the CO2 flux from the state estimate. This is the kind of thing that we're trying to understand. And you see the synoptic scale storms coming around, changing the piston velocity. You see the ice insulating. You see the ocean mesoscale and upwelling. And you also see places where there's huge drawdown because of strong biological sinks. So we can diagnose all these budgets, find out what's important in what location, and really understand these budgets. We can also just simply time average this whole thing, so clean it up and make nice plots that everyone wants to see, and compare that to other products. This is the time mean carbon flux. Totally, it goes from -4 to 4 instead of -6 to 6. There's so much variability that we're trying to deal with, but we do get an average. We compare that to other products. There are differences, there are similarities. We can look at the observations and find out where we think we're doing better than the other products, where we're doing worse. One place where we know we're doing worse is the Argentine Basin. We are getting the Argentine Basin wrong. We understand why, and it's actually a physical circulation problem. But the observations are letting us really evaluate how we're doing. Now, at every annual SOCCOM meeting, we're asked to make a slide like this. What's working, what's not, what's next. I thought I'd share it. And I'll point out what's not working, because I think it's really cool that we have enough observations to know the model biases and where these things are problematic. So we find that the CO2 has in the observed inferred CO2 flux has a seasonal cycle where solubility dominates in the subtropics and biogeochemical, biological processes set the CO2 flux phase in the subpolar oceans. And the transition between the two, as inferred from the observations, is not the same place in the model. So we have enough now to actually start to see this transition location and where it's happening. In general, we can infer that our biological activity is too weak, that the surface PCO2 is a little too high, and pH is a little too low. And then we have problems due to the physical model, too, that we've seen. And I kind of wanted to throw a slide in here, but I didn't have time to. That when we go to higher resolution, we have a NCP too low in the subtropics and in the Argentine basin. And when we go to higher resolution, that problem goes away. I'm going to skip that. That's about another really cool thing that we're getting from the optics. When we start, this is the float optics profile. It's just kind of, each profile that from the SOCCOM array as a function of time, it's over 2 years. You see 2 seasonal cycles where there's big blooms in the summer, kind of goes down. This is POC. We infer POC just from biomass, so we don't have this background. That's why it's different at depth. But our original solution, when we compare to the float inferred POC, was so different. Yet we were finding the nitrate drawdown was equivalent. So we had the right biomass, approximately, but our POC was just nothing like what the floats were seeing. And you can kind of see it here. This is the floats is this green line here. And the original SOCCI solution, BSOCCI solution had this red line. It just had the wrong structure. And this tells us that our original mixed layer parameterization, the way it was handling the mixing of the biomass, was just wrong. We turned up the mixing, and we started becoming more in tune with the floats. And so these biogeochemical measurements are helping us fix the physical components of the model and helping us infer mixing rates and all sorts of information. So there's a synergy going both ways. Running short on time. We do, like I said, try to compare to World Ocean Atlas, see where we're doing better, where we're doing worse. I'm just going to show, this is similar to what I showed before about the seasonal cycle. Now we're in the 1/6 solution, so this is the latest that I have, and I compare it to the December 2017 oxygen, and this is the World Ocean Atlas comparison, and World Ocean Atlas is doing better right now. They're 18% more consistent in December, so it's summertime. As we look at winter, they have a lot less data. They're still beating us at this point, although some of that's just because we're doing bad in the Argentine basin again. But so that's for oxygen. So they're still slightly better than us. Now we go to some of the other things, the things that were really sparse in the past. This is nitrate in December. In the summer they're doing better, 33% more consistent. When I look at the RMS, I think again Argentine basin is one of the issues. But when we go to winter, now we start to win, and so we're getting there. And we can do this with pH, and now you can feel good about yourself. pH. I wrote this is actually GLODAP. Sorry, this is like a different world almost, and this is now there is of course ocean acidification, so that's part of it. But we are 13% more consistent in the summer, where they do have a decent amount of data. You go to the winter, and we're way more consistent. So. We're at the point where we're comparable to these climatologies, plus we have structures of what you'd like to see in the ocean. And I made a movie of us compared to the pH. GLODAP again doesn't move. Oh no, this is DIC. You can infer DIC from the floats and from the model. There's a ton of stuff going on. We like to point out all the structure and how we do need sophisticated mapping methods, so that we can start to infer what's going on, start to estimate what's going on with all these structure. We're not going to have enough floats to capture all the structure. Okay. So I've been talking for the last 10 minutes about holding the model accountable to the data, to validate the model, find out how we can improve it. One thing that I love about what we're doing in SOCCOM is we're also holding the data accountable to the model. Every model data misfit is a probability. We give error bars, and it's a probability of how realistic we think that is. Is it possible or not? And so what we've been doing is every data misfit, we rank the whole thing. So every pH observation has a misfit, has a cost value, and we send to Embari this table saying these are the ones we think are the least likely. And it ends up with a semi-automated QC system where they can now, they do their spike tests and all the things that they do, but then they want to visually inspect the profiles. And now we tell them which ones to look at first. And 19 times out of 20, they say, oh, the model has got the front in the wrong place. But they are finding problems with the data, and they are improving their automated QC or their semi-automated QC and becoming more efficient because these state estimates are not terrible, and we have a good idea of how to quantify. I can change model error when they tell me, oh, no, that place is still wrong. It's still, so we're working together to end up to improve the situation. I'm out of time, but I wanted to reiterate what the state estimate goals are. They are to propagate the observational information with the model dynamics. We're producing a gridded data set to increase accessibility. Some people want to use the raw data, other people want a gridded product. We can provide that. And we're estimating the normal. And we have closed physical budgets. You can go on the website and not just download nitrate maps, but download the full nitrate budget, the full oxygen budget, DIC budget, iron budget. The input and output are freely available. The whole model, you can run it yourself if you'd like. And the code is on GitHub. We're trying to facilitate transfer of tech, whether it be the code or the model itself. And there's a publication where we describe the 2008-2012 solution. Thank you.
So you are not tuning the biogeochemical model at all yet, or are you planning to do that?
So our control vector, as I said, was initial conditions and atmospheric state. That's what we started with. We did experiment with, we picked 8 parameters that are in the biogeochemical model and said, let's control them. But we just tried to control them as a function of x, y. So no time variability, 2D. And we were hoping that they would, sometimes they'd always be, turn, one direction. They're always biased this way or that way, so we could then fill in the. What ended up happening is we'd have bullseyes over here that are red, blue over here. It wasn't constrained enough to.
Yeah, you're overfitting the model.
Or it's not enough. Yeah, there's just not enough information to know what the right value is. So we're thinking about doing it again, where we say just pick this parameter as a function of latitude, or just pick one number. We can do it. We can control anything. We can assimilate anything. It's just we're being very cautious about changing these parameters because we don't want too many degrees of freedom. We want to be able to understand our solution.
But you're basically running a globally fit model, a globally tuned model.
So one thing, before we start doing this 40 var, is we spend about a year manually tuning. Just over and over again. Phone calls to Matt Long saying, we spend a lot of time manually picking these parameters. And then you get as close as you can, and then you have to use this machinery to systematically fine tune. And so, yes, we did tune it ourselves, but we have not been able to yet systematically solve for what the right parameters should be.
Great talk. It's really, I just want to say that I think it's cool that you guys are making all this available. That's awesome. I guess my question is, so you said it several times, so I don't do data assimilation myself. I've heard a bunch of times in your talk and from others that it's not doesn't conserve mass, right?
Well, ours does.
Okay, so then you have these budgets, and you're releasing these budgets, and so I guess my question is, and so maybe if it conserves mass, you could clarify that.
When we say Reanalysis, usually they're like 1 day or 8 day windows. That means they're breaking the physics every 8 days. We say state estimate, it usually means 3 months or longer. We're trying to have closed budgets on at least 2 or 3 months. We're doing a full 5-year closed budget run, and so if we were restarting every 3 months, we would fit the data much quicker. I mean, you wouldn't be able to see the dots at all. It would be, it's really easy. But then, every 3 months, mass would be lost. Right. So we've talked about, does the community want to see us do 2-month, 3-month? But the SOCCOM execs really like the idea of us being able to understand, just get as close as you can and tell us where not to trust the model and be able to close the budget. So that's the mentality. But yeah, you really have these choices to make, balancing controllability versus conservation.
So what you're providing is something
Closed
that's
budgets.
closed and consumed?
Yeah, and it's saucy.ucu/budgets, where we give examples of the budgets too, and you can see each term, and there has been one publication on the DIC budget, but you can get the full fluxes, all this, the influence of sea ice, the dilution effect.
Great, thanks.
Hi, Pierce Buchanan from University of Tasmania. So if you wanted, so you said that you can run it yourself if you wanted to.
Yeah.
So if you wanted to download it and then look at the code and then change the biogeochemistry,
Yeah.
would you break the solutions? Like how much could you change the parameters of the biogeochemical code before you started getting wildly different?
Right. So you could also run the cost function along with it and find out. And so what we did when we published the CO2 flux is we ran this with, we ran our solution, an ensemble of solutions. So not a huge ensemble, but like 12 solutions where we changed things like the biogeochemical model. And we wanted to see how different the mean CO2 flux is and how much our misfit to SOCCAT goes up. So, and then we did a weighted standard deviation. So ones that didn't fit SOCCAT very well didn't really count. Ones that fit it equally well but gave a different CO2 flux would give us a bigger error. And so we got an error bar based on that. And so you can do things where you change the biogeochemical model and see if the cost goes up. And if you get the same cost, if you have the same misfit to the floats with the different biogeochemical model, then it's an equally likely solution. So not only do you get model sensitivity, you also get likelihood that it is a realistic solution.
So you get insight into actual biogeochemical functioning through that.
Yeah, you could change the complexity of the model too. I mean, you can. Yeah.
All right, let's thank Matt again.